Now, in your book there are two different chapters. The first one is, I think, called Current and Resistance. And the next one is called DC Circuits. But we are going to do all of them together because I really don't know why they are two separate chapters. Okay? But let's talk about electrical circuits. So far, what we have done was just electrostatics. All of our charges were immobile. We said, hey, the charges just stay there. They may be distributed on a wire. They may be distributed like a quadrupole in the exam. Okay. Nonetheless, they were not really moving. We didn't care about their motion that much. Now, I'm going to tell a different story. We'll move a little bit away from electrostatics. We'll talk about motion of charges. So what happens is that if I actually have charges in a conductor, if they move with some velocity v, the result is quite different from electrostatics. Now, I said, hey, there are no electric fields inside the conductor. That was my definition of a conductor. So you may say, how do I actually get these charges to move? And I say, hey, I said there are no electrical fields inside the conductor if the system is static, if the system is not moving. Right now, I'm actually looking at the system for moving charges. And for that case, I can and I will have electric fields inside the conductor. All right? Now, the motion of charges, we need to quantify that. Okay? So a simple way to quantify it is to choose some plane and basically cross how many charges cross it per unit time. Okay? If I wait 1 second, 1 million electrons passed. Okay, something like that. Okay? Just as we did for many things, just as we did for velocity, for acceleration, obviously I can turn this into a differential statement. That would be the average current, but the full definition of current, I, will be dq dt, and this is called current or electric current but the physical definition is very simple. It's the amount of charge passing through a, let me call it a surface, per unit time. Let's quickly look at the units. What's the unit for current? Clearly it must be the unit for charge divided by the unit for time, which is coulombs per second. And in electromagnetism, no unit gets unnamed. Everyone gets a name. What's the unit for current? It's amperes. Good. Now, how do I create a current? What do I do? The obvious answer is that if you take a piece of metal, piece of conductor, and if you actually create a potential difference, delta V, across the conductor, charges will go from higher potential to the lower potential, right? So there will be current running through that. But how do I actually create this potential difference? The answer is I actually use a battery. Which is shown by this symbol, two parallel unequal lines. The larger line is the point at higher potential, the other is at the lower potential. But if I actually go ahead and buy a, let's say, AA or AAA battery, that's not what I'll see. This is what I will see. There will be a plus terminal and a minus terminal, right? And it says 1.5 volts here. What does that mean? It means that the plus terminal is 1.5 volts higher electrical potential compared to the minus terminal. Okay, so how does the battery create this potential difference? More importantly, once it actually creates the potential difference, how does it maintain that difference? And what's going on inside this small cylinder that gives me almost always 1.5 volts of difference between the terminals? That's right, that is magic, also known as chemistry. And as you may imagine, there are billions of dollars of research being put into batteries. One of the things that are limiting a lot of devices, including your cellular phones, more importantly cars, is that our batteries are not really very good. Okay. It takes a lot of time to charge them. They do not hold in much energy, at least not enough energy that we can, we have to charge our phones almost every day. Why don't we actually wait for a week? Can we make batteries which will give us enough power so that we don't have to charge our cell phones for a week? Even the top line electrical vehicles like Tesla, their range is around 500 kilometers, if I remember correctly. And that's not very good. That doesn't get you from Ankara to Istanbul without charging. Why? Because the battery does not hold enough energy. Okay. So this is a huge area of research. There are a lot of material scientists, engineers, basic scientists, some physicists trying to improve battery. And demonstrating a battery in the lab is something, and actually making that into a commercial product, turning that into a commercial product, is entirely another issue. Okay, but a lot of chemistry, a lot of nanoscience is being done on batteries nowadays. It's actually quite important. As for the purposes of this course, the battery is just this. It's a magical device with the symbol. There's a plus terminal and a minus terminal, and whatever voltage is written on it, it magically creates this potential difference. Okay? That's the extent of our understanding of batteries in this course. I think in your chemistry course you'll actually get a little bit more. You'll learn that some molecules attract electrons more than others. So you can actually, by changing by a chemical reaction, you can make a certain region at higher potential compared to the others. Okay? Good. Now, what happens if I take a piece of metal and apply a voltage V? Clearly, I will get some current through it. If it's a conductor. What happens if I increase the voltage twice? Well, a lot of things happen, but depending if you have a good conductor, if you have a good metal, most of the time, if you double the voltage, you will actually double the current, right? So we can actually be more specific. We can plot IV curves. So, and it's generally plotted the other way, so let me also do that. So I apply 1 volt, I measure the current, I plot it, I apply 2 volts, I measure the current. I apply minus 1 volt. What does that mean? I reverse the polarity of the battery. I measure something. At 0 volt, probably there is no current. Now, what happens is that there is a, for good metals, most good metals, there is a linear dependence between voltage and current, and the slope between voltage and current is termed as resistance, right? So this is resistance. Now, first of all, realize that this is always an approximation. Okay, I take a good piece of, I don't know, gold. Gold is a very good conductor. I apply 1 volt to it. I'll get, I don't know how many amperes of current. So it will be mostly linear if the voltage is small enough. If I take a very small piece of gold, apply 10,000 volts to it, what will happen? It will melt, right? I mean, it will smoke. Something bad will happen. Okay. For most materials, you'll actually, and there will be some peak voltage that this material is going to saturate. You can have other kinds of behavior. So this V equals Ri, which is Ohm's law, is a good approximation for most conductors. But it's by no means the correct theory of conduction, okay? Although this is known as Ohm's law, all right? So let's see. V equals Ri. So the unit of resistance must be the unit of potential divided by the unit of current. So it's volts per ampere, all right? Which gets the name Ohm, shown by the Greek letter omega, and named as Ohm. Now, when these things were being defined, there was initially some discussion whether it's better to use volt over ampere as a unit, or sometimes it's actually better to think about current divided by voltage. So, just an aside here. Sometimes people write this in another way. They say I is G times V, where G is obviously 1 over R, and it's called not the resistance but conductance. And I think G has the best units. The unit for G, which is ampere over volt, is shown by the following symbol, and it's mho. And I'm not kidding, really. That's Okay. But also there is another name for it. It's also known as Siemens. The appliance manufacturer was actually a person which got his name attached to this unit. He apparently liked conductance more than resistance. Okay. Good. Now, what do we know about resistors? I mean, you have played with them in high school. I imagine you may have even played with them in the lab already. What do? First of all, they respond immediately. Okay, they do not have any memory. They are memoryless devices. This is very different from our capacitors. Capacitors had some memory. They knew if they were charged or not. Resistors, on the other hand, resistance has no memory. So what happens is that they are shown by this wiggly circuit symbol. Whatever voltage you have on a resistor, it immediately responds with current. Now you may ask, to supply this voltage, the battery is running some chemical reactions inside. So it's actually supplying, it's losing some energy. You know, after a while, batteries die. You know, my pen's battery died out in one of our lectures, right? So something is going on. Where is this energy going? What's happening to the energy? This energy is being converted into heat by the resistor. So let's try to understand how much electrical energy is being converted into heat on a resistor. Now, what's the potential difference between the two ends of my resistor? It's V, right? So if I move dq charge from plus terminal to minus terminal, how much work am I doing? V times dq, right? That's the amount of change in energy. How did we define our potential compared to potential energy? Potential energy was V times Q, right? So if I'm moving a small charge dq from one terminal to the other terminal, I must supply energy of V times dq. Now, if I'm doing this in unit in time dt, what is the time derivative of work? What did we call it in physics 101? It's called power. Okay, this is the energy per unit time. The unit was what? Watt. Okay, good. That's a bad joke, but you know, make an effort. So in units, so what's that? V times dq dt, which is V times I. So P, V times I, is the energy converted to heat per unit time across a resistor. Or I can write this in other ways. V is I times R, so this is equal to I square R. Or I can write it as V square over R. And this may be a curse, right? This energy being converted into heat may be a curse. A lot of the energy generated in hydroelectric dams and other generators in Turkey is being lost on the transmission lines. We are literally heating the air, okay? Because Turkey's power transfer structure is quite old and not very well planned. Almost 20% of the energy generated in our plants is lost to this ohmic heating on transmission lines. That's terrible. But sometimes you actually want this heat. If the gas goes off in your apartment, how do you heat yourself? You take an electric heater. And what's the electric heater? You maybe paid 50 or 100 liras for it. But it's just a resistance. It's a big resistor. You plug it in and it heats. So there is not much of complex machinery in there. It's just a big resistor. So it depends. I mean, you may want this ohmic heating or you may try to avoid that. Nonetheless, it's how you convert useful electrical energy into heat, which is not easy to use, right? Good. Let's solve an example. Let's say that I have a battery of V volts and the resistance R is attached to it. And this comes as a package. What I would like to do is, I would like to put another resistance, small r here. How should we choose R so that the power lost on R is maximum? Now this is really a practical concern. Although we don't have DC outlets in our home, if we had a DC outlet, you would read two things on it. You go to the plug there, or even, I have a charger for this laptop. It says two things on it. Let me try to find out. It says, 12 volts and 1 kilo ohm, is that right? So it actually gives me the internal resistance. So most DC power suppliers tell you two things: the voltage, if there is no current running, and internal resistance. Now let's say that I have this DC wall outlet and I want to plug in a resistor so that it heats me the most. How should I choose it? Should I put in a very big resistance so that I square R is large? Or should I put in a very small resistance so that V square over R is large? Right? And I have two formulas for power. Well, let's try to solve this, okay? And I'm relying here that you already know how to solve the simplest circuits like this, okay? Now, I need to find the current here. What is I? What is the total voltage across this? What's the battery voltage? It's V. What is the equivalent resistance? You know this from high school, right? Series resistances just add up, R plus R. So what is the power on just the small resistance, just my heater in my room? It will be I square times R. So it will be V square over R plus R square times R. Now, how do I maximize this power? See, this formula actually tells me how to do it, and I'll do it in a moment. But what happens if I choose a very large resistance, if I almost use a non-conductor there? Then the current will be very small. If the current is very small, then there won't be much power going off. What happens if I almost short circuit, if I actually give a very, very small amount for small r, a small resistor? Then there will be a lot of current, but because my resistance is small, there won't be much power coming out. So I should choose this wisely. How do I find the maximum of a function? I take a derivative. So let's actually take the derivative of this with respect to r. V square is a constant. In the numerator I have r, so this is going to be r plus r square minus r times 2 times r plus r divided by r plus r to the 4th power. And that should be, the derivative should be 0 for maximum power, right? That's how we find maxima of a function. Good. So what does that mean? It means r square plus small r square plus 2rr minus 2rr minus r square is 0. 2r square, excellent. Or, in other words, r square is equal to r square, or small r is equal to capital R. So if I want to obtain maximum power from a circuit with internal resistance R, I should put in a resistor which is equivalent to the internal resistance. Okay, that is somewhat surprising, but fully understandable result. Okay, good. Now, resistance is a nice concept, but it's a little bit too specific. If I take a piece of gold, make it into a nice cylinder, measure its resistance, I'll find one value. Then if I come at with a hammer and hammer it out, make it into a longer cylinder with some dents on it, I'll find another resistance. So the resistance itself is a geometry dependent quantity. But we all keep saying that gold is a good conductor, copper is a good conductor, while plastics are terrible conductors, they don't conduct electricity well. So how should we turn this concept, the geometry dependent concept resistance, into a material property? Okay. And for that, let's look at the microscopics. View of current. So what happens inside the conductor? Now, first, let me give you a warning. I'm going to tell you a story here, and it's just a story. It's not really the truth. Okay? To be able to understand what's really going on inside the conductor, you need to learn quantum mechanics. You need to know what fermions are, what a Fermi surface is, and a lot of other things. However, for a long time, for almost a century or so, people thought conductors were pretty much ideal gases of electrons. Okay. So that's how they modeled it. The model works more or less because it's in correct units. They got the units right. But that's pretty much where it ends. Okay, it's not a very good model of what's really going on inside the conductor. So the classical model inside the conductor is this. you have all these electrons which are free inside the conductor. Now, if I apply an electric field, E, what will happen? All of these electrons, because electrons are negatively charged, they will move opposite to the electric field. They will actually start accelerating, right? They will, because they are under a constant force, they will start accelerating. However, they don't keep on accelerating. Although I said this is almost an ideal gas, it's not quite the ideal gas. There is always some dirt, some impurity inside the metal. And what that does is it acts like a friction force on electrons. Okay. So what happens is that these electrons move as if they are in some sort of fluid. So there is some terminal velocity. It's like jumping off an airplane, but with a parachute. Okay? So what happens is that they actually go to a limiting velocity, which for some reason it's called the drift velocity. Now, if I have n electrons per unit volume, each of them have charge minus E, all of them move with velocity v drift. I'm going to define a new quantity. I'll call it J. J will be n times minus E times v drift. And this is going to be called current density. So inside my conductor, there is this J field. Okay, it's showing me locally, it's a vector field, it's showing me locally where the current, local current is moving. And it's a vector field. It has a direction and a magnitude. And now I'm going to make the big jump here. This current density, if it's a vector field, I can define a flux for it. So I'll take a cross-sectional area, A. I will calculate the flux over a cross-section. What's the flux of this current density? Very simply, it's the current. Right? So you remember electric field gave us electric flux. Similarly, current density gives us current. Now be very careful. Current itself is not a vectorial quantity. If I have a wire, I can talk about the direction of the current, but it's just choosing a direction. It can, at the end of the day, the current may be negative, which means it's flowing in the other direction. That's not a vector. It's like a one-dimensional quantity. Okay? Current density, on the other hand, is a vectorial quantity. Right. So, in general, if I have, let's say, if I really have a wire that carries current I in one direction, and it's uniformly, the current is uniformly distributed through the cross section of area A, the magnitude of current density would be I over A. So the unit of current density is amperes per meter square. Now, how do I define? Now, I went from a global quantity. Current was the total number of charges through my wire, to a microscopic quantity, the current density, which only depends locally on electrons, and it's a vector. So, in general, the more electric field I have, the more current I expect, the more current density I expect. So, people write this in reverse. They say E is rho times J, and rho is called resistivity. So, let's say I have this nice cylinder. Okay. And the uniform electric field E inside. It has an area A and length L. Now, can you tell me what is the potential difference between the two edges of the conductor if electric field is uniform on the inside? E times L, right? It's integral E dot dl, which is going to be just E times L. Good. How about how much current is passing through? At each point I have J, which is going to be 1 over rho times E magnitude. Sorry. So what's the total current? It must be area times current density. So it's going to be A over rho times E magnitude. Then what's delta V over I? E magnitude times L divided by A over rho times E magnitude, or rho L over A, and that's going to be my resistance. The resistance of an object is inversely proportional to cross-sectional area. Does that make sense? Yes, if I have many paths to go, I should have less resistance. And it's linearly proportional to the length of my wire. If I go a longer distance, I expect more scattering to take place, so it will be harder to move, which means I'll have more resistance to flow. But the nice thing here is that we have figured out what geometry does, and all the material property is in terms of the microscopic property, resistivity, which looks at locally how electric field creates a current density. So this is a material property. It's very small for good conductors like copper, gold, and it goes very, very high for poor conductors. If I take a piece of plastic like that, its resistivity will be 10 to 25 in the proper units, while for a conductor its resistivity will be 10 to minus 10. Okay, so there's a huge range of resistivities that are possible. But I can actually look up a table, I can see gold's resistivity, I can look at aluminum's resistivity, and then I can basically design a resistor that will have the required resistance for my circuit. Okay? Let's take a 10-minute break. When we come back, we'll talk more about circuits.